All right, let's just jump right in. Have you ever looked at a massive chemical plant or a sprawling oil refinery and just wondered, how does that thing even work? Well, the answer is kind of hidden in plain sight on these documents called P&IDs. They're the blueprints for our entire industrial world. But honestly, to most people, they just look like some kind of secret code. Today, we're going to crack that code. And hey, it's not just you and me. Even the pros get tripped up. This quote, it's from an engineer over on Reddit, and man, you can just feel the frustration, right? Even with years of experience, these diagrams can be a real fight. So what gives? Why is this supposedly standard language often so darn confusing? I mean, look at this. At first glance, it's just a chaotic mess of lines, squiggles, and letters. But what you're actually looking at is a super detailed map. It shows exactly how everything flows, where all the equipment goes, and what little gadgets are keeping the whole thing from blowing up. That complexity, well, that's the whole point. But it's also the biggest headache. So, to make sense of all this, here's the plan. First, we're going to figure out why this language is so all over the place. Then we'll learn the basic symbols. After that, the fun part. We'll check out some big, expensive screw-ups. We'll talk about getting the details just right, the trouble with old-school diagrams, and finally, we'll see how tech is coming to the rescue. So, that big question. Why all the inconsistency? Well, you've got to remember, these things have been around forever. We're talking decades, way before we had fancy digital files and global standards. Back in the day, companies were just copy and paste symbols from old hand-drawn plans. Whatever one firm used became their way of doing things. And those little quirks just got passed down year after year. Okay, so what is a P&ID, really? Think of it like a subway map. It's not drawn to scale, right? It doesn't show you the actual streets above ground. Its only job is to show you how the stations, or in this case, the pumps, pipes, and controls, are all connected, and how you get from point A to point B. It's the logic of the system. And just like any map, to read it, you've got to know the symbols. Every little circle, every line, every square, it all means something specific. It's the vocabulary of this whole language. And wow, there are a lot of them. I mean, just look at this. You've got symbols for all kinds of valves, for pumps, for sensors that check the temperature or pressure. Every single one is like its own word in this crazy visual dictionary. Now, don't get me wrong, people have tried to clean this mess up. Big organizations like ISO and PIP have these huge rule books, like ISO 1062-2 is basically the official dictionary for these symbols. But, and it's a big but, you've got history. So many plants are old. They were built way before everyone agreed on these standards, so they're still stuck using their own weird, company-specific symbol. Okay, so now you know the basics. Let's talk about why getting this language right is so important. We're going to look at a few super common mistakes, little things on a drawing that can turn into massive, catastrophic disasters in the real world. All right, mistake number 1. This one's a classic, starving the pump. It's all about putting one single valve in the wrong spot. Get it wrong, and you can absolutely destroy a piece of equipment that costs a fortune. So here's how it goes down. Look at the wrong way on the left. The valve is before the pump. Now imagine that valve closes, but the pump's still chugging along. Uh-oh. It's got nothing to pump, it's running dry. Now look at the right way. The valve is after the pump. Simple, right? Now if that valve shuts, no big deal, the pump stays full of liquid, nice and safe. So what happens when you starve a pump? Something nasty called cavitation. Basically, tiny bubbles form in the liquid and then they collapse with incredible force inside the pump. It's like a million tiny explosions going off, creating these crazy vibrations that literally eat the metal away. It just shreds the equipment from the inside out. All from one simple, totally preventable mistake. Okay, on to disaster number 2. This one's about those giant mixers you see in big tanks. They're called agitators. And the big no-no? Turning one on when it's not sitting in liquid. It sounds easy to avoid, but if the system isn't designed to prevent it, it's a full-blown safety nightmare waiting to happen. So how do you stop that from happening? The fix is actually so simple, it's brilliant. You just add a level sensor. But, and this is the whole key, where you put it is everything. You have to place that sensor above the mixer blades. That way, the system is smart enough to check, hey, is there enough liquid in here before it even thinks about turning on the motor? And there's a really good reason for that. It all comes down to physics. See, these agitators are built to work against the heavy resistance of liquid. Take that liquid away, and there's nothing holding it back. It can spin way, way faster than it's supposed to. And if it hits just the right speed, the harmonic frequency, the whole thing starts to shake uncontrollably. We're talking vibrations so violent they can rip the entire machine right off its foundation, wrecking the tank and putting anyone nearby in serious danger. And for our last big mistake, this one is just pure forgetfulness, but it might be the most dangerous one yet. It's simply forgetting to put in safety valves. I mean, this is safety 101. It's an absolute must-have for anything under pressure. Let me say it again. Safety valves are non-negotiable. Think of them as the last line of defense. If things go sideways and the pressure inside a tank starts climbing and climbing, these valves pop open all by themselves and let that pressure out safely. They are literally the thing that stops a tank from becoming a bomb. And in the US, it's not optional. It's the law. Anything over 3 psig, you have to have one, period. So we've seen some specific screw-ups, but there's a bigger idea here, kind of a Goldilocks problem in P&ID design. You can't have too little information, that's dangerous, but you also can't have too much, that's just a waste of money. It's this constant battle between under-specification and over-specification. Let's look at two sides of that coin. On the left, under-specification. You've got a reactor that's making its own heat, and you only have one temperature sensor? That's a ticking time bomb. What if that sensor fails? You need a backup, like a pressure sensor. Then on the right, you've got over-specification. It's a simple water tank. You don't need sensors for level, temperature, and pressure. That's just throwing money away and making things way more complicated than they need to be. Okay, so even if the original design was perfect, just working with these things can be a pain, especially the old ones. These old-school diagrams can create a whole new world of problems for today's engineers. Yeah, the list of problems is pretty long. You've got those wacky, inconsistent symbols we talked about. You might be squinting at a scan of an old hand-drawn blueprint. But the real killer? The paper copies are almost always out of date. These plants are constantly changing. If you're looking at a drawing from 5 years ago, you could be basing a critical decision on a pipe that doesn't even exist anymore. Which, of course, brings us to the future. So what do? We have millions of these super important drawings that are old, confusing, and out of date. Well, the answer, more and more, is technology. We're finally moving away from dead paper and into smart digital data. And this is pretty cool. We're now using AI to read these old drawings. Basically, the computer looks at a little piece of the diagram, it traces all the lines to pull out the individual symbols. And here's where the magic happens. A special kind of AI, a neural network, looks at each shape and tries to match it against a huge library of symbols it already knows. It's learning to recognize a pump or a valve, no matter how it was drawn. We're literally teaching a computer to speak P&ID, turning a static picture into a smart, searchable database. So that leaves us with one big final thought. P&IDs, this is the language we use to build and run pretty much everything. And as our world gets more and more complex, as the stakes get higher and higher, we absolutely have to get better at speaking it. The need for a clear, universal language has never been more critical. So whether it's by creating better standards or building smarter technology, making sure everyone is fluent in this language, well, that's one of the biggest challenges facing engineers today.